All right, this is the second section or the second part of the chapter 11 videos that you're going to be watching today. And yes, there are going to be questions as we go through. So I do want to make sure that you understand you're supposed to be writing down the question number and then the actual answer, just A, B, C, D, whatever that answer might be for you. Okay? So without further ado, we start with phase changes. All right, so on this diagram in front of you, you see some exothermic and endothermic processes that are color-coded. I suggest you study this if you don't remember this, but this is just a process that kind of indicates when we go from one phase to another, what happens. Do we have to put energy in? Does energy get pulled out? And if that happens, the phase change itself has a name as well. So moving from solid to liquid, of course, we're going to melt. Moving from liquid to solid, we would be freezing. Moving from liquid to gas, we'd be vaporizing. Moving from gas to liquid, we'd be condensing. Moving from gas straight to solid is called deposition. And moving from solid straight to gas is called sublimation. Okay, and we are going to study these in a little bit closer detail here in a second. First, we're going to talk about the energy changes that can be associated with different changes of state. The first is going to be the heat of fusion. This is going to be the amount of energy that is required. Yes, think energy, joules, kilojoules per mole, if you will, that is required to change a solid from its melting point to at its melting point to a liquid. So this is the amount of energy that has to be put in for the phase change itself to actually occur at that particular point. So this is the heat of fusion, which is of course going to be going from a solid to a liquid. The next is going to be heat of vaporization, which goes from a liquid to a gas. This is going to be the energy required to go from that liquid to a gas, and this is the amount that's got to be put in that phase change, for that phase change to occur. Next and last is going to be the heat of sublimation. So this is if we wanted to go straight from a solid to a gas, or vice versa. Now, all of these heats are going to be reversible. Just to go from one direction to another is not enough. If we wanted to, we could go the opposite way. Just remember that when we go the opposite way, typically what happens is the sign changes. All right. From there, this is one of our first types of diagrams. There are two types of diagrams we're going to talk about. This is a temperature heat diagram that kind of tells us how much energy or how much heat has to be added to different parts of a substance's phase journey, if you will, from solid to liquid to gas. And at each point, there's different pieces of information. This particular diagram corresponds with water. So 0 degrees is where, 0 degrees is where the ice and liquid phases are going to kind of meld. In this particular point, not all of the substance will be either one or the other, but once all of the substance has changed from solid to liquid or from liquid to solid, then we are in a new, different part of this curve. So for instance, if I started here at point A, and I wanted to heat my ice up so that it could become the next phase, I would have to generate enough heat to get it to go from whatever temperature. I'm so sorry, I don't know why my mouse keeps doing that. I would have to put in enough heat to generate however much I need to heat the ice from the negative 25 degrees that it started at up to 0. Then I would see a flattened part of this curve while I waited for the ice to move from the solid phase into the liquid phase, and this is where they'll simultaneously exist. Then in order to move from the ice solid phase up to the to get all the way through the liquid phase up to the gas phase, then we have to put in a certain amount of energy to go from the 0 to 100 degrees Celsius. Once I've put in that amount of energy, then I have to put in enough energy to get all of the liquid to become the gas. After all of the liquid has become the gas, then, and that phase change is referred to as vaporization, or evaporation, if you will, then I can actually heat the remaining product, that gas product, and call that, in its gas phase, of course, steam. Now, at each point, what's happening is by putting in more and more energy, we are pulling molecules apart. Starting down here, by putting in more energy, we're moving the molecules more and more as we do it, and then eventually they're going to be able to separate. The substance itself during a phase change will stay the same temperature. So we know we're undergoing a phase change if the temperature is stagnant. All right, and here's your first question of the lecture. They are kind of interspersed throughout this lecture. They're not just all at the end like they were in the previous video. So make sure you're actually watching through and you're grabbing them as we go. This question, once you're done, you can go ahead and you can move on. So pause and then unpause. All right, next topic is going to be on vapor pressure. And so vapor pressure is just going to be the relation to what is the pressure above a liquid of a specific product. Now, this has to do with what happens at the actual interface of the liquid as it's doing its phase change. At any temperature, though, we're going to have that molecules in a liquid are able to escape and become gas molecules. Now, the fraction of the molecules that can actually do this changes with temperature. And this is something we've discussed in the past in our gases chapter. But for now, what we want to know is the more molecules that actually become gases from the liquid phase, the more pressure is going to increase. And the pressure that they exert is going to be referred to as the vapor pressure of the liquid. Now, the liquid and vapor states are going to eventually have this dynamic equilibrium going on, and we're going to talk a lot about equilibrium next semester. But this dynamic equilibrium, this idea that as one thing is created as far as a gas, like so as the liquid particles become gas, at that exact same rate, the gas molecules are becoming liquid molecules and condensing. Whatever point this is, where this dynamic equilibrium is reached, we can measure the pressure and call it the vapor pressure of the liquid. Now, this vapor pressure is directly related to boiling point, in that we can graph vapor pressures versus temperatures of different substances in order to determine what their boiling point is at our specific pressure. So in other words, the normal boiling point versus a boiling point. So a boiling point is going to be where a vapor pressure equals the atmospheric pressure under which the thing is undergoing its change. The normal boiling point, more specifically, is going to be the temperature where the vapor pressure is 760 torr. Why 760 torr? Because 760 torr is 1 atmosphere, also known as the most standard pressure that is measured in a laboratory or at sea level, if you will. Okay. When we take some different information and we manipulate graphed data, right? So in our previous, we saw vapor pressure versus temperature. If we manipulate data and take the natural log of pressure versus 1 over temperature, we get a straight line. That straight line is going to give us information about the vapor pressure under certain conditions. In fact, we're going to use what we call the Clausius-Clapeyron equation to actually do this. And here we say that the natural log of pressure is going to equal the heat of vaporization divided by RT plus C, C being a constant. Okay, now this is a way of measuring the heat of vaporization of a liquid, of any liquid, very useful for various reasons. Okay, phase diagrams. Last big topic in this chapter, or second to last big topic in this chapter if you count the liquid crystals. So in our phase diagrams, these are going to display pressure versus temperature. So you see pressure is always going to be on the Y, temperature is always going to be on the X. And these different phase diagrams, first thing we need to learn is how to read them. So here we see the 3 phases, solid, liquid, and gas. And we see lines. Across those lines are phase changes. So when a solid wants to become a liquid, it has to melt. And at a specific pressure, that may be different. So in other words, if I'm at a low pressure and a low temperature, then I know that a solid melting and becoming a liquid is going to be easier as far as energy requirements and where it's going to happen versus maybe higher temperatures and higher pressures. We can also interpret this as the lower the pressure, the lower the temperature, right? So as we want to go from a solid to gas specifically will only happen at low pressures and low temperatures according to these diagrams. Okay, so some other points that we have to describe are the triple point and the critical point, and we'll talk a little bit more about those here in a second. But I just want you to see that these diagrams are super useful for describing where different substances are at different pressures and temperatures. There's also going to be equilibria. That dynamic equilibrium we talked about doesn't just exist in vapor pressure situations, it also exists when things are trying to undergo those phase changes. Okay, so the liquid vapor interface is going to be referred to at the triple point, where all 3 states, solid, liquid, and gas, equally exist only at that one point. Okay, that will end at the critical point, also known as where the liquid and vapor are going to become a supercritical fluid. So critical point is going to be super useful for knowing when liquids and gases are indistinguishable from each other anymore. We get that supercritical fluid, which is a very interesting fluid to study if you're interested. And then we get over here, down here at the triple point, that's where we start that liquid-gas interface where all three of the phases are going to be present at equilibrium, meaning that no one phase is dominant. So when we look at something at the triple point, it has a really cool, look to it, and they're very interesting. There's a video I'm going to post for you guys to watch about hexane at its triple point, and what happens is it just rapidly moves through solid, liquid, gases. Like they're indistinguishable from each other. Okay? All right, so this one is going to be your next question. Go ahead and pause it, answer your question on your paper. This is question number 2 for this video. And when you're done, you can go ahead and move on to question number 3, which is going to be this one. So, of course, again, get written down, question 3, and then your answer. When you're done, we're going to move on. Talking more about phase diagrams. So next thing to look at is where different phase changes actually occur in phase diagrams. So between the line of the liquid and gas, we can see that there is a boiling point, and that boiling point is going to be along this specific red line. Okay, and it changes with different pressures, and because as pressure goes up, temperature also goes up. And this is going to be something to kind of remember from our gas laws, chapter 10. Okay, between liquid and solid, we're going to see the melting freezing point. So as pressure goes up, of course, temperature does increase, not at the same rate as when it happens with a liquid and a gas, but still does happen. But the line is where the solid will become a liquid and where the liquid will become a solid, depending on which energy transition is actually happening. Okay. Below a triple point, our substances cannot exist in the liquid state. So that's kind of a big takeaway here. Anything below the triple point cannot be a liquid. It could be a solid or a gas, and those are the only two. This line typically for most substances is going to be very short and very difficult to achieve, the sublimation deposition phase, just because the lowest pressures are very hard to create safely. All right, here's your next question. This one's going to actually ask you to interpret what we've just been talking about as far as phase changes. When you're done, you can move on. We have a few more left. We're going to talk about the phase diagram of water specifically. You may or may not have noticed that water has a very odd-looking phase diagram. In fact, it's one of the few that instead of having a liquid gas line that goes like this, has an inverted parabola. Very odd. Of course, we've talked about how water is very weird. We've talked about many reasons why water is weird. This is no exception. Water has a very high critical temperature, so a very high point where liquid and gas become supercritical fluid. And it also has a very, I would say, moderately low triple point as well, where this can occur. So again, very low pressure, low temperature. A lot of this has to do with what we talked about at the beginning of this chapter, which involves the intermolecular forces. Strongest intermolecular forces present in water, of course. So the slope of that line being negative is just very, very odd. What it means is that as we increase pressure, the water goes from a solid to a liquid. Just as we increase pressure, the temperature below the melting point, so think like, here. Instead of this line going backwards is very odd. It's not supposed to do that. So as we increase pressure, we're supposed to see solid become liquid. But as we do that in water, we actually see liquid become solid. Very odd. All right. At higher altitudes, where pressure is lower, the boiling point of water. Please interpret the diagram. When you're done, you can go ahead and you move on. All right. Phase diagram for carbon dioxide is just kind of another oddball, but it does have the exact same type of movement as far as solid liquid is concerned, as most things do. Has a pretty predictable critical point. Mostly the thing that's weird about carbon dioxide is that it cannot be a liquid below a pretty high pressure. So CO2 is very typically found as a gas, and we all know that. And so it's just interesting to note that, like, when you're looking at something like carbon dioxide, it cannot exist as a liquid at all below a pressure of about 5 atmospheres. And when we say that it sublimes, we talk about things like dry ice. Okay? All right, so liquid crystals are going to be a very specific type of interaction that we have to talk about within liquids. And there are a few different types of liquid crystals that we will mention. There are 3 specifically, I'm pretty sure it's 3. We will talk about 3 of them specifically because those 3 are the most common, and those are the only 3 that we care to know about. When we are talking about liquid crystals, this has to do with how the phase change doesn't occur quite predictably, and we get like what we call an intermediate state. And this intermediate crystals state is going to have some characteristics of the liquid phase and some of the solid phase. And so in doing this, we're going to see that there are 3 different types of order that this can happen in. So the far left diagram is just going to be a straight liquid phase, no crystals, just molecules kind of randomly arranged with each other. And then the first type of crystalline phase that we can have are nematic liquid crystals, where they are ordered along axes. In our case, we would typically say y-axes, but it really depends on which direction this thing is facing. So if you're thinking like a test tube, it would be pointing up and down, and that's the nematic liquid crystalline phase. The symplectic liquid crystals are going to be ordered in 2 dimensions, and they're going to be in layers, so they're a little bit more ordered, if you will. And they are going to be ordered in either an A or a C way. The A way has them all perpendicular to the layer planes. The C way has them inclined related to the planes, as you can see in these diagrams. The very last type that we're going to talk about are cholesteryl liquid crystals. These are nematic-like in that they're not necessarily ordered as much, but they are going to relate to the nematic crystals in that they typically all point in the same direction. And these are going to be layers upon layers that all kind of point in different directions. Anywhere from a 45 to 90 degree angle can be seen here. Okay. And the very last thing to kind of mention about liquid crystals is that they can actually typically be seen by putting light through them. So that's the major way that liquid crystals have been studied in the past. And they exhibit different changes in terms of their colors when temperatures change. And by changes in color, a lot of times what we mean is like they kind of become more cloudy or white versus whatever color they are in their resting phase. Okay? All right, and this is your last question. Which of the types is not a type of liquid crystal? All right, when you're done, you're done. You have a great day.